Hi everyone. So today we're going to take a look at modeling exponential functions. So we're going to be looking at, again, our exponential growth and decay idea, but we're going to introduce an equation that's going to help us model percent increase and decreases and things like that. So when we're doing an exponential growth and decay, we need the percentage of growth or decay, and that's going to be R. R is going to be your percentage of growth or decay. Now, if your growth, you're going to be positive. If it's decay, it means you're going to subtract. Okay, so when I say growth, you're going to add R, and then you're going to, if it's decay, you're going to subtract R. So your growth factor is basically B, okay? So B is still going to be your number that's being taken to the exponent, but you're going to get that by going 1 plus your R. So remember, it's going to be your percent. Make sure we write our percents as decimals. If we're decaying, if we're decreasing, then your B is going to be 1 minus R, okay? Or 1 plus negative R, okay? So you're going to subtract the percentage from 1, and that's going to give you your growth or our decay factor. Okay? So here's our formula. A of t equals A times 1 plus R to the t. Now that's 1 plus would be plus for growth and then 1 minus R for decay, but R would be negative. Okay, so keep in mind that A of t means the amount that we have after a certain amount of time. A is your starting amount. So if you have $100 in a bank account, that would be A. Or if we had a population of 50 fish, that's your starting amount. So whatever your starting amount is, that is A. So think of it as where the graph crosses the y-axis. When B is 0, you have no growth nor decay. Or, sorry, what's being 0 years, not B is 0. The number of years would be 0. Okay, your starting position. Okay, so R is going to be our percentage. Okay, and that's going to be growth or decay. Again, if it's growth, we're going to add. If it's decay, we're going to subtract. Okay, and T is going to be our time. How long are we doing this? How long are we going to look at the number of fish, and so on and so forth. Okay, all right, so let's take a look at our problem. So we have a population of a certain animal species decreases at a rate of 3.5% per year. You've counted 80 animals in the habitat you are studying. Okay, is the exponential model seem reasonable for this? Yes, because it's decreasing at a percentage. So we are going to be using the amount after time equals A times 1 plus R to the t formula. All right, so we need different parts. Okay, so we need our initial amount of population, which is 80. Okay, so that's going to give you your A. Okay, is the rate of change positive or negative? So our rate, it says decreases, okay, at a rate of 3.5%. So that's going to be a negative, okay, because we're decreasing. Okay, so our R is going to be negative 0.035. All right, so our rate of change is negative 0.035. So we're going to write our model that represents this particular problem, which is going to be a decay problem because it is negative. Our rate is negative. So our amount after time It's going to equal our initial amount, which is 80, 1 minus 0.035 to the t, because we don't know our time yet. Okay, so this is 80, 1 minus 0.035, 0.965. Okay, so we're going to try and graph that. So the best way I can tell you to do that is use Desmos, unless you want to pick some points and put them in. We know it's going to cross the y-axis at 80 because that is going to be, t is going to be 0 time. Okay, so let's go to Desmos, okay, and put this in. All right, so we're going to do y equals 80 parentheses 0.965 to the x. So we're just going to put our x up there. Okay. All right. It's not showing up here because our y-intercept is all the way up here at 80. So let's scroll all the way up. Up, there it is. Okay, so I'm just going to pinch this down. So here is our graph. Okay, so it crosses the y-axis at 80. Okay, decreasing. Okay, so if I was like down here, we could take a table. Let's take a look at a table. Here it is. Oh, no. Sorry. Let me go back. Okay, it was creating a table. I thought it was going to give us the table. All right. Okay, so here's 80. And we could, okay, take a look at where it crosses different places. Okay, so I wanted like that point 20. So around there. Okay, there is no other intercepts or anything like that, so it's not going to show up right away. All right. Okay, so this would be all the way up at 80. Okay, I'm going by tens. Okay, so it would just come down, cross, and go like that. All right, so we need to estimate the number of years until the population first drops below 15 animals. Okay, so I want to know, when is my y value 15? So I'm going to come over here to my Desmos and see if I can figure that out. So here's 20. Remember, y, this guy down here, the x-axis is going to be the number of years. So 20 animals is about 40 years. So 15 may be about 50 years. Okay, so let's check the table. If I put in 50, okay, what is my y value? I'm going to get it to work. Obviously, I'm not going to get that to work. All right, so I'm thinking about 50 years. Okay. All right, because you would want to look at the graph and kind of estimate where is the y value going to be 15 years, 15 animals. All right, so let's take a look at this one. So you invested $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest, and the amount of money, how much money will you have when you graduate? All right, so 6th grade, graduate in 12th grade. So how many years is that? It's going to be 6. So in 6 years. All right, so let's write our information. So we're going to go amount after time. It's equal to how much money we started with, which is 1,000. Okay, now, are we increasing or decreasing here? We're going to be increasing. So we have to make this 1 plus 0.05 to the t. So 1,000, 1.05 time. Okay, because we're just writing a function. All right, so how much money are we going to have when we graduate? So we're going to put in 6 for time. Okay, we should get $1,340.10. Okay. All right, so in both of these problems, one was a decay, one was a growth. We added or subtracted the 0.05. All right, in this case, we added it. All right, so let's take a look at this next one. Okay, here's a problem with this. We're looking at the Iberian lynx in 2003 and 2004. How much, if it continues and the population decreases exponentially, how many lynx will be there in 2014? The problem is that I don't have R. Okay, so we're going to have to figure that out. So if you want to think of this as a percent increase or decrease, I like to think of it as new minus old divided by old. Okay, so it's the difference of the y's divided by the original y. So that's how we're going to figure out our percent. So we're going to have, we started with 100, or we have 130. The original amount was 150, and then we're going to divide that by 150. Okay. And so when we do that, what do we get there? Negative 0.2. Okay, so it's decreasing at about 20% per year. And we're going to say that's a constant decrease. So we're going to write our model. So again, 2003 is going to be our original amount, 150. So amount after time is equal to 150. 1 minus 0.2 to the t, or 150 times 0.8 to the t. It's amount after time. Okay, so we're going to find the population 2014. So that's 11 years since the original amount. So we're going to do 11 years. So our amount after 11 years is 150.8 to the 11th. Okay, so I got about 13. So that means there'll be about 13 lynx. Okay, if it was still decreasing, I wonder what it would be in now, if that's true. All right, so again, we're going to want to use our Desmos to figure out where population would be about 30. Okay, so if we go back into Desmos, let's clear that one out. So it was y equals 150. Again, we're not going to see it right away because of the y-intercept being 150 times 0.8 to the x. Okay. All right, so we can see this particular right now. Okay, so about 30, be probably around 7 years. Okay, because 30 is, this is how many are, the y-axis is how many are there, and the x-axis is the number of years. Okay, so that was 2003, that is 17 years. If the rate of change is the same, 17 years would be, looks like there's only about 4, if the percent is just, if there's no interaction. All right, so we said about 30 left would be 8 years. All right, let me know if you have any questions, guys. And remember, we're going to stay in to keep each other safe. Have a great day.